So today is the second part of the Conversational AI for human-robot interaction. And today I will talk a bit more about the human-robot interaction part. So Oliver gave a very nice introduction to the Conversational AI part, and I'll focus on the latter for today. So I'll start with a short recap, and then I want to talk about two projects that we had. One is the MAMA project, which is human-robot interaction, and the other one is the GRID project, which was smart intelligent building, which we think is still relevant for things that we do here. And I will show you the approach that we use to implement the systems that we used for this and how it all worked in the end. So let's start with a short recap, just so you're still familiar with terminology. So this is the general pipeline that Oliver talked about. It all starts with the user saying something. It then goes into the automated speech recognition, or ASR, something like "I want Chinese food," which is then transformed by the natural language understanding component into some form of logic expression. Like this is an inform act where the food type is Chinese. So this becomes a dialogue act, which goes into the dialogue manager. The dialogue manager tries to figure out what to reply, creates another logic representation, like another dialogue act, like recommend restaurant 127, for example, which goes then into the natural language generation and is turned into a string, which is then synthesized by the text-to-speech component. As Oliver already hinted at, now in human-robot interaction, we don't just have words, but we might also have graphics or robot expressions or movement and so forth. And we need to execute all of this on the robot. We need to synchronize this. This just makes everything a little more difficult, but also a little more rich in this multimodal interaction. So the general approach of Alana was that we have a bunch of different sources that we weave together, like news, Reddit, wiki, and so forth. There's something called coherence, where we track the topic that we're currently talking about with the user, track named entities and the user's interests, and try to drive the conversation as well. Like if the conversation stalls, if none of the news sources or Reddit or something has a reply, then coherence just says, "So remember, we can talk about music as well," for example. And we also have this user model that we also talked about last time, which keeps track of all these preferences and the conversation history and so forth. The whole thing looks like this. So we have our users that talk to a device, which goes into the main hub. Then we have a bunch of bots that might produce an answer to this, or to whatever the user said. We have a selection strategy that selects the best reply according to some metric, and we have some post-processing where, for example, the name is inserted and templates are filled in and so forth. So the important thing for today is to keep in mind that it's like an ensemble of different bots that all compete for the attention of the user, or for the right to talk to the user, basically. So all of them produce an answer, and somehow we select a response either based on a priority, or it can be learned from data as well. We have different bots. There are rule-based bots like the coherence bot or the persona bot. So if someone says this, then I reply this always, right? There might be like a bit of a random element where you have several templates for that you can choose to reply with, and then you select one randomly, but it's still a rather deterministic process. And then you have retrieval bots like the wiki bot, which reads Wikipedia and summarizes it, or the Reddit bot and the news bot, the news API, which scours the internet and so forth. So these are the main two categories of bots that we're going to look at today as well to achieve the smart building interaction and the human-robot interaction as well. Then the main thing is, how do we do the selection in the end, right? So this selection strategy becomes very important. And the selection strategy, as I said, usually multiple bots have an answer. Then there's a neural approach to rank all of this. But in the two projects that I will talk about, we actually heavily used priorities. So we just said, if a specific bot has a reply, then this bot will be chosen as well, because for specific application domains, if you have tasks or want to talk about something relating to a specific building because you're in that building, then you want to make sure that this information is actually also prioritized over other information that you might find on Wikipedia that is also related. This can be trained as well. I'll talk about all of this, so I won't spend too much time on this. But this is just so you have a bit of a background again, or a bit of a recap of how the whole system works. So today I want to talk about two specific applications that we had. One was in the grid building. This is the grid building in the top right here, which is a new building on our campus. And actually, Veronica and Nancy were involved in developing a system for this grid building that is able to talk to users about all kinds of things relating to the building that I will show you in a bit. And then we had a project called Mummer with this pepper robot. So I will have a lot of pepper robots in this in these slides, just because we used them for this previous project. But all of this has been implemented in ROS, so it's the robot is just plug and play, right? It's easily transferable. So just imagine the pepper would be Ari, and then we're already a bit closer to the Spring project. So the tasks that we had in these projects, the Mama project was aimed to create a helpful and entertaining shopping mall guide robot, right? So in the shopping malls, you have like info booths and people who work there who might be able to help you to find a shoe shop or to find where Primark is and so forth. And the idea was to have a robot help with this, while it can also be entertaining. The entertaining part we never really defined in the project idea, but in the end it boiled down to being entertaining through dialogue, right? So being able to chat about likes and dislikes of people, like chat about their favorite music or their favorite sports. And since Mummer was in Finland, the favorite sport for everybody is ice hockey, obviously. We had all kinds of ideas of playing games like hide and seek, which we relatively early on decided not to do, because it's way too easy to play hide and seek with a robot, right? The robot will never find you again, and the robot will get lost, and the robot will just be too easy to find. So we decided not to play any games, but to have the entertaining part being the dialogue. In the grid building, we aimed to create a helpful kind of virtual persona for building. So if you have seen 2001 Space Odyssey, and you know HAL, like this. So we wanted to go for something similar, a little less murderous maybe. But this kind of embodying voice, or this embodying persona that lives inside the building that you can talk to, you can ask for directions, you can ask where to get a coffee, you can ask them where to find a PC and so forth. So these were the two applications. They have certain similarities, like both of them are still able to have open domain dialogue, because we didn't want to restrict this. Actually, we just submitted a paper about this open domain dialogue in the grid building, where it actually shows that people are less willing to talk about personal likes and dislikes in public. But yeah, we can talk about that later if you're interested. But it's still able to talk about anything in the world. Both of these systems give guidance to locations, and they are both not necessarily as a focus point like in the Mama project, but even in the grid project, try to be entertaining to a certain point. And they give specific information to the location, like the mall opening times or the building opening times and so forth. The main difference is that in the Mama project, the system was embodied. And therefore, we needed to run several the software in several different locations. Like everybody had a robot in their own lab, and we had the robot in the shopping mall. We had to run it in several different languages, mainly English and Finnish, but also French for our Swiss partner. And the Mama project also included lengthy physical interactions, like the robot was able to move around and point at certain things, which takes some time. And when you just look at dialogue, everything is instantaneous, right? So the main problem was how to combine all of this and synchronize them and still make it somewhat entertaining and believable. So let's start with the grid project. In the grid projects, the approach was we created a separate instance of Alana. So we just spawned a separate instance on the server. And we specialized the ensemble of bots, like the blue boxes on the right here, to make them specific to the building. Like we added a resource bot that would tell you where to find a free PC. Like this is a teaching building, and it has a lot of computing rooms or computing labs. So people always come there and try to find a PC. We have a directions bot that will tell you where to get a coffee or where to find the computing lab if you haven't been. And a specialized building persona that knows about opening times and the history of the building and so forth. So the whole system looked like this. This is just a different visualization of Alana. So we have the usual Alana bots down here. Then this is the main hub. And we used the Google Home Mini or several Google Home Minis that were talking to the user. And these are the special bots. So we had to have an ethics bot, for example, that would tell people this is a research project and your voice will not be recorded, but we will keep a transcript of these things. And only if they are okay with that, then we would actually start the interaction. Then we have these specialized bots. We have the directions bot, the resource spot, the event spot. The event spot I didn't mention, but you can ask like, what's going on today in the boardroom, for example, and it would be able to tell you based on the calendar. So all of this was still running on a centralized remote server. We have a priority list that gives priority to the building-specific bots. There's a custom NLU that runs inside these bots. So for the resources bot, the directions bot, and the events bot, the NLU tries to extract the intent, like what the person wants to do, and the entity, like what are they talking about. And this is handled inside these bots. This is not handled by the main NLU. And all of this was implemented as a Google action. So it's running on Google Home Mini, so you can also run it on your phone and so forth. So you can already see that this replaces Alexa. So it's basically all Alana does is produce a string, right? It takes a string and it produces a string. And what you put on the other end of these two strings doesn't really matter, right? So this is why we can use it for so many different applications. So for the direction giving, which might be something we have to do in Spring as well, depending on how we interpret the use case. The layout of the building was represented as a graph. So you can see this here, where we have something called the Business and Enterprise Hub, which has several meeting rooms that are accessible from it. These are connected via zones, and this was used to generate the actual route guidance. But this route guidance was not egocentric, right? So normally if you ask someone for directions, they will tell you, oh yeah, you see this door over there, you just go through it and then you go left. Or from here you go straight and then right. But this requires that you need to know where you actually currently are. And where the person is looking at. So we had several problems with that in the grid project because we don't know which Google Home actually triggered Alana, because Google removed the device IDs from their devices due to GDPR to make them less identifiable. So we actually can't tell which device is used to give the directions. So they were global directions, like you go to the stairs and then you go up and left, for example, because all our devices were downstairs. But you can't say, oh, you go straight from here and then left and right. So this was one difference. That's one difficulty that we have. And then the other bots that we had were information retrieval bots. Like the Wikipedia bot, for example. There was the resources bot, which parses a web page for available PCs, and the events bot, which parses a calendar for events. And all of them have their custom natural language generation to create the utterance afterwards, and so forth. So this was just a quick overview of one way to customize Alana. So basically having a central server that where you create a new instance, and then you assume that everything you do is just independent of the device location, the actual device, and you don't want to execute any physical actions and so forth. So this is one way of easily extending Alana to do all of this. Now the big problem is when you add embodiment to all of this, right? So compared to a Google Home, Ari has a head, arms, eyes, it can move about, it has a tablet. So all of this means we have to create multimodal output. But also the expectations towards this type of dialogue, if you talk to a robot, are different. As I said before, the most obvious would be that you give egocentric directions, right? You teach a robot actually more as a person than you do a Google Home Mini when it comes to dialogue. So you would expect it to behave more like a person as well, and to have similar skills to a person. And when you ask a person for directions, you would naturally expect them that they give you egocentric directions, which means from your current location. But also you use different types of language when you talk to a robot. So a lot of people, when they see a Google Home, they always start their sentence with "Okay, Google," right? Whereas when you talk to a robot, we wouldn't expect people to start every sentence with "Hey, Ari," and therefore this is one example. But it also changes the way you talk to it. You are more happy to talk about personal things and so forth. So we have to deal with different language that we need to understand. And then each different robot might have different abilities as well. So one robot might be able to give you directions because it actually has a map of where it is. One robot might be able to drive around. One robot might be able to point. So there's not just one method that fits all to fulfill a given task on a robot. So one robot might have arms, and another robot might be able to drive around. So one robot might be able to drive to a location from where it wants to explain the route. One robot might want to point to where it wants to explain the route. So we have to trigger all of this without knowing the actual robot, because main Alana still runs on a server somewhere. But we still have to know the capabilities of the robot, and we have to control the actions of the robot. And we have to support other languages than English, right? So depending on which country the robot is in, the language has to be different. Like in our case, it has to be French. And in the case of the Mama project before, it had to be Finnish, which is a horrendous language. It's horrendously difficult. So I'm very glad that we switched to French, which at least is a little easier than Finnish. But that also means that we need localized versions of the NLU and the NLG, which then all boils down to that we need a specialized NLU and that it's not possible to run everything on a remote server. So we have to have an approach of distributed dialogue management. So parts of the dialogue management will be done remotely on the server, but other parts, when it comes to executing actions on the robots that involve physical tasks, will be done on the robot itself. And Alana has to be able to communicate with all of this, and we have to synchronize all of these tasks as well. So let's start with how to identify the actual task that we want to create. I already said that we need to build a specialized NLU. So we start with that, and then afterwards we come to the distributed dialogue management. So the specialized NLU, this is the image that you've seen before. We have the user who says something like, for example, Misa und Kenkakaupa, which is Finnish, which goes into the ASR, and then we need a natural language understanding, which produces some form of dialogue act, so some form of logical representation of what the user just said. There's very little data for the Finnish language. So building an NLU, especially if it's based on deep learning, without much data and without having Finnish speakers developing the actual NLU and being able to check the training data and being able to check the results, is a very hard task. And it's not a very rewarding task because Finnish is very much a niche language, right? There's only 5 million people in the whole world who speak Finnish. So we tried to adopt a different approach, in that we had a translation component in between, which translates Misa und Kenkakaupa to where's the shoe shop, which can then be interpreted by the natural language understanding. There's a problem with that though. So looking at this example that Oliver gave the last time already, this is just a different one. Where can I find Mini Money? Mini Money is a shop, and basically just means small money. It's just how you would pronounce it with a Finnish accent, Mini Money. And this we want to translate it to a request of locating Mini Money, which is a sort entity where I am trying to find this and so forth. But since we needed this to work in different languages, we use Google Translate. Since Finnish is a very niche language, Google Translate is not very good for it either. So this led to a lot of incorrect sentences, like grammatically incorrect, that don't make much sense in English. And therefore we required robust recognition. So actually the system that Oliver showed you the last time, which is this, was especially built with this in mind, that we are able to take correct English samples and incorrect English samples based on Google translations from Finnish, use them all for training, and then be able to still generate these kinds of structures, even based on grammatically incorrect sentences afterwards, and still be able to extract the request for locating and the sort entity afterwards. So I won't go into too much detail because this is not my work and I don't exactly know how it works. There's a paper on this if you're interested in it, which was published at SIGDIAL last year, that explains this. And this was the first step towards us being able to actually handle all of these interactions. So let's talk about the thing that I actually was mostly involved in, which is the dialogue management. So mostly dialogue management still is done using state machines, which is why I have this nice picture here, even if it's learned. But when it comes to robot behaviors, you also often use state machines still, especially when it's high-level behaviors that require several actions to be executed. So we wanted an approach that is compatible with this, because also state machines do not require any a priori data that you need to train them on, which is hard to get, especially in HRI. So our requirements to this dialogue management Whereas I said before, on the one hand, that it needed to handle distributed dialogue management, meaning on the remote server and on the robot itself. It needs to handle multi-turn execution, so you might have tasks that require several actions to be executed. Each action might require to talk to the user to clarify something. I have an example of that later as well. It requires to interleave dialogue and physical actions, like dialogue actions being just producing a sentence to say, and physical actions, for example, being driving somewhere and talking or gesturing. We wanted to be able to interleave several strands of execution. So that means if you're currently in a task, we don't want the system to be trapped in the task. So if I ask you a yes or no question, I still want the user to be able to just switch topic and ask about anything else and start a new task, because otherwise it feels very restrictive. And we want to give the user the most freedom that we can when deciding what they want to talk about. And we need to have a back channel between several ROS action servers, for example, because that's what we will be using to run our tasks or our behaviors, and the user. So all of this needs to go via Alana, and therefore we need a back channel that keeps track of this. And as I said, a database learning approach is difficult, especially in the beginning of a project, because exploration is very costly, right? So either you create a user simulation where you simulate a user based on your best guess or experience, or based on data, and then you train your system on this, or you build something like a state machine. But just putting a robot there that just tries to learn on the fly is just very frustrating for people most of the time. And we wanted to maintain the open domain functionality, as this was our entertainment factor that we had. So let's start with the general idea of distributed dialogue management between our Pepper and the cloud, which is Alana. For this, we developed something we called the taskbot. So the taskbot lives here in the slightly cut down bot ensemble, just for size purposes. So it's just one of the bots, right? So it competes with all the other ones for the attention of the user. And therefore, we need a selection strategy that makes sure the taskbot is selected and so forth. But again, this is done via priorities. Like it was in the grid project. So if the taskbot produces an answer, then the taskbot will be selected, because the natural language understanding found the user wants to execute a task now, or this is something, or the user said something related to a task. So therefore, we want to have the taskbot answer, and we don't want to give them something from Wikipedia about where to find a shoe shop. So this taskbot actually handles the starting and the execution of the task from the dialogue side. So the taskbot keeps track of the running tasks. So we have a stack which is filled with the tasks, and the tasks are removed once they're complete. And it passes questions that ROS actions might have to the user, and then passes the replies back to the dialogue management running on the robot. And it does all the natural language generation. So this is something I already mentioned in the work group 3 meeting, where I talked about this taskbot briefly as well. So one of the main important part is that even if your components, right? So you just have a very simple thing, like let's say the robot drives down a corridor and needs to go left, right? Most people say, oh yeah, I have access to the TTS. So I'm just saying, I'm turning left now. And that's just one sentence that I verbalize. No one needs to know about this, because it will most likely never come up in conversation again. So they just synthesize this, and then the dialogue management doesn't know about it, because they just synthesized it and bypassed Alana. But then the person might ask and say, why? Right? So if the robot says, I turn left, the person asks why. The why will go to Alana, and Alana will reply to something that Alana thinks you were talking about, but which is not the case, because something else was synthesizing text in between. So now all of a sudden you have the robot giving an unintelligent answer that makes it look like it doesn't work properly. So in order to make sure that all dialogue history is in a shared location, all the natural language generation is handled inside this bot. So if you have any component that needs to talk to the user, even if it's just verbalizing something, it should all go through the same component. So we are able to create proper dialogue out of this. This dialog bot we try to make as easy as possible, which boiled down to a large YAML configuration file. So you define tasks like you do here. This is the task root description. When this is triggered via dialog, then Alana sends a JSON that looks like this. And you have different statuses. So this task might send Alana that it wants to disambiguate something, where it sends it some value. So if you have a list of things like I'm looking for a shoe shop, and might say, or do you mean shop A, shop B, shop C? So this verbalization is done via this, and then Alana resolves this and will return the shop that the person said it was. Or you have a clarification where someone might say, do you see Starbucks? Because Starbucks might be on the way to the shoe shop and you want to say it's Starbucks, you go left. So you send a status called clarification.landmark with the value Starbucks. Alana synthesizes this into do you see Starbucks? Then listens for yes and no with some highly sophisticated regex, as you can see here. So a lot of the stuff in dialogue still boils down to regex once in a while. So if you know regex, then you have good chances in dialogue. It's a superpower that not many people have, but they are highly sought after. And then it either returns yes or no, like a Boolean value, and then your component knows that it does that, and then can continue and so forth. So this is what keeps track of the dialogue or of the task state on Alana's side, and then it needs to communicate with the robot. So on the one side, we have Alana here on the right. Again, this is yet another way of visualizing Alana. This is when three different people create the same kind of image. They all look a bit different. But you see here, we have the task bots, we have the task stack, and we have an Alana interface. Actually, the Alana interface is not remote, but it's local to the robot. So this box should be a bit lower. But all of this runs remotely on the server. And then on the other side, we have our locally running components, which is the planning and execution framework and our ROS action service, which I will talk about in a bit. And then we have something called the arbiter, which arbitrates the information flow to either go to Alana or go to the TTS or go to the planner, or come from the planner to the Alana and then to the TTS and so forth. So this is why it's called the arbiter as well. And then obviously we have our robot here, which can be any kind of robots, but in this case it's a pepper. So let's talk about the connecting component. Yes, does someone have a question?
The ASR is locally to the pepper, yes?
No, the ASR in this case was also Google ASR. The TTS was local, but the ASR was Google ASR, because the ASR on Pepper is Nuance, and Nuance is very bad. Nuance doesn't give you the full transcript of the sentence. So the problem with the local ASR on the robot was that we can do keyword spotting, like if you're looking for a specific word that works. But if you want to do open domain dialogue, like you want to figure out what the person really is talking about instead of just spotting a keyword, then you need the whole sentence. And at least I'm not aware of an ASR at the moment that can run locally that is able to give you a full transcript of the sentence.
So actually the entire speech was transferred from the local Pepper to the remote server?
Yes, to the Google Cloud, and then it came back as a string, and then we transferred it to Alana.
And what was the latency for this?
The latency was about a second. So actually, what we did on the robot is, you see that the tablet on the robot, right? So we had, like, when you have an Alexa at home, you know, it has this blue ring around it that like pulses while it tries to transcribe your sentence. So we had like a little cogwheels on the tablet of the Pepper when it was processing your speech, just to give people some feedback that the robots actually understood what they said and is currently processing it, which helped people a lot to make the interaction less annoying. Because before we had that, people were never sure if the robot actually understood what they said, if it's doing something, and so forth. So with this lag, you actually have to think about how to mitigate the consequences of it.
Thank you.
You're welcome. But yeah, there was one way of doing it. So actually, the Pepper robot on the tablet was displaying when it was listening to someone. So it had a green tablet saying listening. And it had a yellow tablet with spinning cogwheels when it was processing the speech, and it had a red tablet saying speaking when it was speaking, because we weren't able to allow barge in, so we weren't able, or the robot wasn't able to listen to the person while it was speaking, for several technical reasons, mainly because we didn't have an audio processing partner. So maybe we'll be able to do this in spring, but that is up to Sharon and his team, and I can't really make any promises about this. So this arbitration unit, to talk about the connecting components, it handles as I said, it handles the communication between Alana and the robot and the planner, and it does that via dynamically creating ROS services and topics to communicate with specific components. Because there might be ROS actions that run several times, some concurrently, but for different tasks, because one task might still be open and a new one is started. And I will show you an example of this on the next slide. And the arbiter also tracks the execution status of tasks, right? So while Alana has the task stack and tracks the currently running tasks, so which task is the latest that was started, the arbiter actually tracks the currently running tasks in no specific order, because the order is given by the dialog. But it knows which plans are active and which servers are active and so forth. But let's talk a bit about this. One component might be running at several times, because this is all about interleaving tasks. So let's say you have an example. I've given this before, so you've seen this before, but I want to talk about this in a little more detail now. Let's say someone asks how to get coffee, for example. How do I get to Starbucks? And then the system might reply, or do you see the red sign, which might be the first landmark on the way to Starbucks, which we want to describe to, which we want to use to describe the way with. But then before this question is answered, the user actually notices that they have a greater need for going to the toilet first. So we start a separate thread of execution, which is this red one, which still is direction giving. So it's the same plan, but it's a different location, right? So where here you wanted to go to X, like Starbucks, now you want to go to the toilet. So it's a different strand of execution, but of the same action service. And then it goes through the whole thing, like asking if it can see a landmark, then if you can take the stairs, because the toilets might be upstairs or downstairs. And then once everything is confirmed, it gives the route description and the task is finished.
Christian?
Yes?
Sorry, how do you know that you have to start a new thread?
This is done in the task bot. So the task bots, or the NLU, gives you this: where can I find mini money? Where can I find Starbucks? Where can I find the toilets? And whenever you get something like this, it goes to the task bot, and the task bot takes this as a trigger to start the task route description with a given entity, mini money, Starbucks, or the toilet. So whenever you hear something like this, then the task bot decides, now I have to start this new task. So it's very simple. If someone says this, then I start a new task.
Okay, so it's rule based.
Yes, it's very deterministic and very rule based. Yes,
Okay.
but then if you have like a question in between, then this is not picked up by the NLU as I want to go somewhere, but just as a yes. So this doesn't start a new task, but this relates to an old task or to the most recent running task, and therefore is then transported back. But I have another slide that might explain that a little better. And then the user might come back to the blue execution task by confirming that they can see the red sign. So this is some string matching here, where you match this utterance to this utterance to identify that it belongs to the blue task, and then the task bot continues with the next step in the route description. Then there might be some off-script things which doesn't have to do anything with task execution. And then in the end, there might be like a completely different task where we take a selfie with the robots, which have the pepper pose for pictures. So this is the reason why we need to dynamically generate services and topics, because in here, these little dots represent ROS actions, for example, right? But this action is the same as this action. So both action servers are called the same, they just have different arguments. So now we need to know which action server to forward this yes to. So looking at this, if we have our arbiter, and we have the user that talks to Alana in some formal way, and Alana talking to the arbiter, then the user might say, how can I get to X? And then the system should reply to, you see the red sign. So the arbiter starts plan I, which is give directions to the coffee shop. This plan starts a task, which might be a ROS action server, and starts several other tasks until the nth task then generates some user output because it needs to talk to the person. Because task n, for example, wants to generate the route description, so it needs to know where to start the route description from. So it asks the user, do you see the red sign? Because this might be the starting point. And then this is transferred to the arbiter, to Alana, to the user, and then verbalized to the user. So it's basically Alana will then reply or will pass the reply of the user and forward it again. But until then, this task n is waiting, right? So this task is paused and it doesn't do anything. But now our user actually says, oh, I actually need to go to the toilet first, right? So Alana finds this as a new task in the task bot, sends it to the arbiter. So the arbiter starts a second task, which is plan I+1 with trying to go to the toilet. Again, this starts task I until it reaches task n, which is the same task as this task n, and then asks it, do you see area Y, which is this bit. And then it is also waiting for a reply from the user, right? Because the user hasn't replied to this utterance yet, and it hasn't replied to this utterance yet. But then, as I said, both of these tasks might be the same ROS action. So both of them might be the action server called /give directions. So now we have to figure out which one to reply to. So if now the user says yes, right, which task do we send this yes to? And the system that we developed for Mummer does this by, as I said, dynamically creating services that uniquely identify this task. And Alana has a task stack, so Alana always replies to the most recent question that it asked. And the most recent question is this one. And even though both of these servers are called the same, since we uniquely identify them via services and topics, the reply is actually forwarded to task n. And then the execution continues on this task with task n+1, where this task asks the person if they can take the stairs, and then this task is waiting. And this is how the whole execution progresses. So this one is still waiting, and when we reach this part, I didn't go as far as to explain all of this here. This waiting would be resolved, and then this task, this plan would spawn the next task, and so forth. So this is how the execution works in principle. If you want to know more about how all of this works, I wrote some documentation and usage examples that you can find here. The slides are online as well. And we will upload the code for all of this once we have a shared Git repository. So this is about the dialogue management. But now, how do we actually execute all these tasks, right? How do we decide the sequence of tasks, and how do we manage the execution of them? This is done via Petri Nets. So this is a generic Petri Net that I found on Wikipedia. The source for this is already published and available. There's documentation as well in the paper, so you can have a look at that too. But let me just talk you through it quickly in the remainder of the time. So Petri Nets is a logical state transition model, or a mathematical state transition model. So you can express the whole Petri Net in a matrix vector multiplication, which makes it nice because it means you can very easily build automata or state transition automata with it. So Petri Net defines places called P, transitions called T, and arcs called A, that you can then put into a net, which is the places, transitions, and arcs, and the actual Petri Net then takes this net N and also combines it with a marking. A marking are these black dots in these circles. So these are called execution tokens or markings, and weights for the arcs. So you see these little numbers under the arc. This one has a 2, for example, and this one has a 1. So this is a place, this is a transition. So this place has a marking of 3. So it has 3 execution tokens. And since this arc has a weight of 2, that means that whenever there's at least 2 execution tokens in this place, it means this transition becomes active. And this weight also means that when this transition fires, it consumes 2 of the execution tokens in this place. Whereas this number means this is the number of execution tokens that it produces in the other place, in here. So if this is time step I, then at time step I plus 1, after the transition fires, I consumed 2 of the tokens in this place, and I created 1 new token in this place. So this could be the other way around, right? If this would be 1 and this would be 2, then I would consume 1 here and create 2 there, right? So the number of tokens consumed and created is only dependent on the weights. It's not dependent on the initial amount of tokens that you have. So this is going to be useful for the next slides where we talk a bit about concurrent execution. But this is how a Petri Net works in principle. So you have places, transitions, arcs, markings, and weights. So now the best thing, as I hinted at, in Petri Nets is that they inherently, or that they make it very easy to model concurrency. So looking at this example, where we have our place at time t1, where we have 1 execution token here, and we have an arc that doesn't have a weight. If it doesn't have a weight, that's implicitly always 1. So that means I need 1 execution token here for this transition to fire. And then out of this transition, I have 2 arcs. All of these have a weight of 1 as well. That means at T2, when both of these places, or when this transition fired, both of these places will have 1 execution token, like the square in here. I just use different shapes to mark the passage of time. Have execution tokens in here, and then again, this has a weight of 1. And at time t3. Both of these transitions fire, and each of them has an execution token. And then this is at time t4. So why does this make it easy to handle concurrency? Because imagine one of these transitions. Imagine this transition now is a ROS action, right? Which takes 5 seconds. And this is a ROS action which takes 2 seconds. So now this ROS action finishes executing earlier than this one. So this transition occurs earlier. So there will be an execution token here before there will be an execution token here. But only if both of these arcs have or if both of these places have the right amounts of execution tokens, like one each in this case, this transition will become active. So each place that has an arc into a transition has to have the right amount of execution tokens in it based on the weight for this transition to fire. So this transition will not fire until both this and this place have been reached. So that means it will wait after this transition has occurred for this transition to finish as well, and only then this transition will fire and it will finish execution. So this is how Petri Nets, in a mathematical way, and in an easy to implement way, are able to synchronize the execution of your tasks to a level where you wait for all tasks that should be executed concurrently to finish before you finish the execution of any follow-up tasks. So this is normally rather hard to do in state machines, whereas Petri Nets give you this automatically. So now out of this, I developed Petri Net Machines, which is basically a Petri Net version of deterministic finite state machines. Because these are still used in a plethora of robotic systems, because getting data is hard and just making a state machine is much easier. But these state machines also have other downfalls that Petri Nets are able to handle with, because Petri Nets, you can mathematically prove that the goal state is reachable from all states, and that every state itself is reachable, which is very hard to do in if you use ROS Smash, for example, or any other finite state machine. You can't really prove that you can reach the goal from every state. And they make it hard to handle concurrency. So in these Petri Net machines, as I call them, if you look at the definition of a finite state machine, you have your input symbols, you have your set of states, you have a start state, a transition function, and a set of goal states, where the transition function is just the Cartesian product of the states and the input symbols that lead to a new state. And the PNM is pretty similar. We also have input symbols. We have our Petri Net instead of our states. We have our initial marking. We have goal places, and we have a different transition method, where our transition method is based on the input symbols, the current marking, and the transitions that should be active based on the marking, and that then leads to the transitions that should be active based on all three of them, right? So if you look at this, in here, this transition, for example, is active based on the marking, but in our Petri Net machines, we also make it based on the outcome of our ROS action, which could be our input symbols. So each transition actually looks like this. We have our action that is executed, and then the place, and then we have three different outcomes, right? We have failure, interrupt, and success, which are the three outcomes of a ROS action server. And depending on the actual outcome of the ROS action server and the marking in here, only one of these will be active. And this helps you to decide the control flow of your program. So if success, you want to do something. If it's failed, you want to do something else, for example. This, as I said, uses ROS action servers, and it also includes the outcome into our transition function. All of this is auto-generated, so you don't have to define your Petri Net yourself. You basically define a domain file and you define a plan file, where we're currently working on replacing the manually defined domain file with the outcomes of just a generic planner. and then it auto-generates this Petri net for you and executes it for you. So this is what it looks like. Where we have our domain, it looks a bit like it's inspired by PDDL, where we have a dummy server that has parameters, it has certain effects, or we have a wait server which has preconditions. And all of these effects and preconditions are checked automatically by the Petri net, so it automatically includes places and transitions that fire if these preconditions are true or false, or if these effects have been achieved or not. And then we define a plan where we just have either sequential execution or we have concurrent actions. So now here, these two wait actions will be executed at the same time, and also these other two wait actions. So that looks a bit like this, where we have our dummy server, we have our transition, we concurrently execute these, but we also concurrently execute these, and we only finish our overall execution once all of these has finished. And you can already see that wait 3 seconds, so this will fire at the same time, but then this waits for longer, and so forth. But only after the wait 6 is over, the execution and the final will finally finish afterwards. So this is done. Then each action is translated into one of these constructs, which I showed you before for the action servers with success, interrupt, and failure, which just maps to your server application, which is identified based on its name. So if your action is called task root description, your server also has to be called task root description. All arguments in the goal of the server are passed in automatically. All the results are read and saved in a local knowledge base. There's versions of the server that are able to communicate with Alana to ask questions. And all of this is done. And if you have a look at the documentation, that gives an example of how to build a quiz game that runs on Alana using the task server. Once all the code is there, you can have a go at doing that yourself and creating your own Alana quiz game to play with it a little and see how all of this works. So all of this this is all done by using the local knowledge base for argument passing and the global knowledge base, which in our case is the user in Alana, but you can also use a database, an ontology, etc. Like in the Mama project, we had an ontology for root descriptions. And in addition, you can also add recovery behaviors, like you can fail the plan, you can retry an action, you can skip an action, you can ask the user for help, and so forth. So all of this is made in a rather modular way, or at least I try to, and allows you to define your own execution patterns. And hopefully we'll replace it with a planner soon, so you don't have to do that manually either. So finally, after all the Petri Net stuff, the last thing that won't take long because I've already taken up a lot of time is how do we do route descriptions in the shopping mall, which might be relevant to the Spring project as well, because there we have our hospital and we are embodied in the physical world. So this was actually not our work, but we could think about something similar in the shopping mall, where we had an ontology of connected buildings. Like this is a research building in Las in Toulouse, where they actually developed this approach, where they had corridors and doors. And we had a 3D model of the environment. This is the actual shopping mall. It's a Blender model of it. And this was used for creating the route descriptions, but it was also used for reasoning about what the person, the robot, can see. Like if you tell them, oh, you see the sign over there, because you know the person is looking in that direction, and in your 3D model, in that direction, and the view cone of the person is a sign. So you should be able to use that sign to describe the directions. So analyzing the head angle and the view cone of the person in our 3D model, we were able to take the perspective of that person and then use that for route descriptions. And finally, there's a little video of a very handsome guy talking to a robot And this has two different examples, one where it's just text-based, where the robot just gives a route description and pointing, and one where the robot also moves doing that. And all of that was using the system that I described so far. So we'll just play that and shut up a bit because it will have audio, I believe. I hope you can hear that. I don't think you can. No, I muted the audio because it has subtitles. Okay, very good. Because I wasn't sure if it works. So I asked it if it can show me the way to Bella Roma, which is one of our favorite restaurants in the shopping mall. They have a very nice Finnish interpretation of pizza, and it points in that direction because Bella Roma is up here. It's also called Denny's Diner and Bella Roma. So the robot points into the location, which is also based on the 3D model. And then confirms if I've seen it, and then gives me the route description to actually go up there because there's another entrance. So all of this was a bit confused, but this was still early days of development. And then I can't get my mouse. Now there's a different shop where the robot starts the route description from a point where the shop is not visible. So this is another hands-on developer of ours. And he asks to go to Ilju Pileri, which I'm not sure what they sell anymore, but it doesn't matter really. But the robot figured out that the shop is not visible based on the 3D model from the location where they're at. So the robot actually goes over to the location where the shop is visible. It's hard to see, but the shop is down here. You can just about see the ILOP sign here. And now the robots will point to the shop and look at the person to see if the person looked towards the shop and so forth, and then gives the route description. And this is something that we did and something that we could also think of doing similarly or differently in this project. But all of this was using the Petri Net and distributed dialogue management that I talked about. And that's it. So yeah, I talked for quite some time, but I hope you're not all asleep by now. So if you have any questions, please let me know. And thank you very much.